Hello, folks. Rashid here. Thank you so much for joining. In our microarchitecture series, we are building a hardware block diagram, right? For our all the 37 base RV32I instructions. And today we are going to create microarchitecture block diagram or finish it for majority of the I type instruction. So just a quick overview what the instruction that we have done so far and what are the instructions we're going to do. So we started with, if you remember, the very first microarchitecture we did was add I, right? And then we did load word and store word. Because with this one, we were able to assign a value to a register. And with this one, we were able to load something from the memory into the register. With this one, store something from the register into the memory. Then we did R type instruction, the yellow ones. And today we are going to do the I-type instructions, which are all the green ones, but we're not going to do all of them. We are going to do the mathematical or logical type. So if you notice this and or exclusive or I, so all these I-type instructions have I in it because they only use one source register. The other is not, data is not coming from the register, it's coming from within the instruction. There's an immediate value, okay? That's 12-bit. So then we have shift, then we have set less than, okay? The other I type, which we are going to do later, few videos down in this playlist, is a load byte unsigned, half word unsigned, and things, and this JALR. Okay, so if you remember the I type instruction, if you have watched the architecture series, then you should be familiar with it. But I'm going to do a very quick review. So this is our 32-bit instruction format for the I type. So you can see we have, okay, where are my glasses? Oh, I don't have my glasses. Okay, so you see that we have first 7-bit for the opcode, then 5 bits for the destination register, which is where the result of the operation is going to be written. Then we have 3 bits for func3, what we call. Then the first source register or the only source register is 5 bits for that. And then we have 12 bits for the immediate. Some of the bits which are for the RS2 are taken by the immediate. You're aware of that, right? So yeah, that's it. If you look at this, you can see that for all the immediate or all the I-type instructions, the opcode decimal is always 19. The differentiation between different I-type instruction is with this func3. So 0, 2, 3, 4, 6, 7, 1. But you notice that this shift right, so you have to make a little bigger, can't see it. Shift right, left, right, and arithmetic. So logical and arithmetic of shift right, and both are immediate versions. They have the same func355. So question is, how are we going to differentiate between the two? I don't know if I cover this in the I-type architecture, but that's okay. We're going to cover now. So bit number 30 and 31. So for the shift instructions, we cannot shift more than like 31 bits, right? If it's 32-bit. If we shift by 30, the whole number is gone. So in order to shift maximum, say 32, how many bits we need? We only need 5 bits. So in the shift instruction, we see we don't really, the immediate is actually represents the number by which we need to shift this RS1 by right, left. And this number, we only need lower 5 bits only. The upper 7 bits we don't need. So bit number 30 is actually used to differentiate between these two. 0 is for this one and 1 is for this one. Understand that? So that's an important thing that we need to put in our architecture diagram. Okay, so what we are going to do, how we going to do. So if you remember I don't know, do I need to go through these examples? So these are, so let's go into this architecture. This is the architecture we have so far. All the instructions that we have done prior to this, okay, and I turn them into black and gray because so that any new wiring that I do in red, okay. So yeah, I should have put this in black as well, but so we can do a little bit of review of that. But what you will find out that this is the architecture, the microarchitecture, I should say, that we have created so far. And if you remember, we did implement add I, load word type instructions. So this architecture actually pretty much covers all the instructions, those I type instruction that I was telling you that we were going to implement. So actually we don't need to create any, don't need to make any change. The only thing I noticed, and I probably didn't have, was that for the shift instructions, okay, if it's a shift, those two, remember this one that I just explained, the number 5, logical and arithmetic, that is the code that even for those cases, that differentiation happens. So this ALU control, the way some of the change will happen in the control side, so because it's using bit 13. So inside this we will have a change, and so in the Python code that I'm going to update inside the controller there will be change, but in this picture overall, as because this is a more like a block diagram, we're not going to see any change. You'll probably be wondering why I'm not creating block diagram inside a controller. We will have a lot of combination circuits. So if for example, so from I will refine this diagram a little bit in the future videos, but what's really happening is once this address comes at the input of instruction memory, the output that we get is 32-bit instruction. So what I'm showing here with arrow, what this one takes is opcode 7 bits, func 3 bits, and func 7, those 7 bits. These three type of different things from the instruction we actually provide to the controller. Then controllers have a lot of multiplexers. And the way we're going to implement is with the system Verilog high level instructs like if opcode, is this, func 3, func 7 is this, then generate, set this signal 1, else is 0. So if you can think of this as we're going to, if you really create it with a hand, it will be a truth table. So you put all these are the inputs and all these are outputs, and you, based on different combination, you set some of them 1 and 0. And then we're going to create a gates for each one as a function of this. Okay, so this goes back to those sum of min terms or product of sum terms type of logic that we created in the truth table. But we're not going to work at the gate level. That's the beauty of the system Verilog languages or hardware description languages, that you don't really need to code at the gate level. So we will make use of higher level constructs such as if or case statements, and we will simply generate this logic. So there will be a lot of gates here, but we will be using a simplified constructs in system Verilog. And actually in Python, I will show you the code later on. We are using the same thing. If this, do this. So later on, I will give all those ifs to AI and say, okay, give me an optimized system Verilog code for that. I will review that, and when we give that to synthesis tool, synthesis is going to create all those gates for you. So we will make use of that. Okay. All right. So change in control. I should probably take an on. Change within control, but nothing else in the picture that you see. This is very much going to implement all the instruction we had, and these are all the instruction. I've just put a add I x0 plus whatever number you put. Maximum is 12 bits, right? It can be signed and unsigned. So you add x0 and 10, put the output in x1. And you AND this x1, the content of x1 bitwise with the number 15, the equivalent of that in hexadecimal. These are decimal numbers I put. Okay, and the output will go to x2. And similarly, this is our shift x1, content of x1 by left by 3. Okay, shift right, logical x1, shift to the right side and put zeros on the most significant places. And arithmetic, you shift it with the sign into the most significant bits. Set if x1 is less than -5, okay, then what we do is we set this to 1, else 0. So similarly, this one for unsigned. So you understand the concept, right? So these are all the instructions, and I think that's it. That's it. That's all for this video. So in the next one, we will start looking into actually some of the control, or actually the next video I would like to show you. We will implement some of the flags there, which I don't have it, and I think that's where I want to explain you what are those flags. So ALU generates a result which we have here, but it also generates a flag. And those flag details, what are those flags, how are those generated, what is the importance of those, and that is going to be the topic for the next video, 1 or 2. Okay, that's it for now. I will see you very soon. Bye.